In the chronicles of mechanized warfare, there exists a singular, defining epoch when the age-old struggle between the projectile and the plate achieved a terrifying, unprecedented zenith. For generations, the main battle tank reigned supreme, its dominance assured by ever thicker slabs of rolled homogeneous armor steel.
Yet, the advent of the shaped charge, the high-explosive anti-tank heat warhead in the mid-20th century, rendered these monolithic fortifications utterly obsolete, piercing steel as though it were mere parchment. This catastrophic vulnerability necessitated a radical, paradigm-shattering response, an alchemic transformation of the tank's very skin. That response was Chobham armor, the genesis of composite protection, shrouded in the deepest secrecy, and a technology that redefined the meaning of armored survivability. The genesis of this revolution lies in the quiet, methodical laboratories of the United Kingdom, specifically at the Fighting Vehicles Research and Development Establishment, FVRDE, at Chobham Common in the late 1960s.
The challenge was multifaceted. Defeat the searing jet of plasma generated by a heat warhead, and simultaneously resist the colossal kinetic energy of newly developed high-velocity armor-piercing discarding sabot APFSDS rounds. Steel, even the most advanced alloys, could only slow these threats. It could not negate them. The solution lay not in uniformity, but in complexity, in heterogeneity.
Chobham was, and remains, an intensely classified, non-explosive reactive armor system built upon the principle of layered complexity. It is not simply steel, but a matrix, a sophisticated sandwich of materials, often involving high-hardness steel alloys, ceramics, and various non-metallic composites, all bound together in precise, non-uniform angles and thicknesses. Imagine the impact of a heat jet traveling at hypersonic speeds, designed to exploit the homogeneity of steel.
Chobham armor introduces calculated chaos. As the molten jet penetrates the initial layers, it encounters ceramics, materials of extraordinary hardness, often synthetic sapphire or boron carbide. These ceramics fracture under the immense pressure, but crucially, their structural failure is highly advantageous.
The shattering introduces lateral stresses and non-linear paths, disrupting the focused energy of the jet, causing it to yaw, fragment, and dissipate its destructive power long before reaching the crew compartment. This mechanism, known as obliquity and fragmentation, is the fundamental principle that renders traditional shaped charges significantly less effective.
Simultaneously, Chobham had to be engineered to defeat the brute force of kinetic energy penetrators, the long, slender darts of tungsten or depleted uranium. Here, the layered construction utilizes the principle of differential impedance. The alternating layers of hard, brittle ceramics and tough, ductile metals, like specialized steel, or in later versions titanium, force the incoming penetrator to expend maximum energy. The ceramic shatters the penetrator's tip, and the following layers of ductile metal catch and distort the now damaged rod, absorbing energy through plastic deformation. The total package maximizes the time and distance required for a penetrator to traverse the armor, optimizing the protective effect by ensuring that the armor's thickness-to-density ratio works against the projectile's mechanics. The global impact of this British invention was instantaneous and profound.
When deployed on the Challenger 1 in the early 1980s, and most famously integrated into the American M1 Abrams series, where it evolved into specialized variants known colloquially as Dorchester armor, Chobham became the gold standard of protection.
The psychological and practical implications for tank crews were revolutionary.
Suddenly, they were shielded by something fundamentally different from the armor of their predecessors. A technological shield so effective that it could withstand multiple hits from the most potent contemporary threats. The very concept of the tank battlefield changed. It was no longer a matter of simply hitting the enemy. It was a matter whether the enemy possessed the exponentially more complex munitions required to breach this new, meticulously engineered skin.
However, the adoption of Chobham presented monumental logistical and design challenges. The material's composition is immensely dense, and its structure demands specific volumetric requirements, leading to staggering weight increases. A modern Abrams or Challenger II weighs upward of 60 to 75 tons, a large portion of which is dedicated solely to this dense, classified armor matrix.
This weight necessitates powerful engines, complex transmissions, and places enormous strain on infrastructure, bridge classifications, and tactical mobility. Yet this trade-off was deemed absolutely necessary. The cost of losing a crew and a multi-million-dollar asset far outweighs the logistical headaches of hauling a metallic behemoth across the battlefield. Furthermore, the secretive nature of Chobham ensures a constant shadow arms race.
Each nation possessing the technology rigorously guards its specific matrix composition, often changing the internal layers and material pairings with every major upgrade package. This perpetual refinement is driven by intelligence gathering and ballistic testing against captured or replicated enemy munitions. The armor on the M1A1 is different from the M1A2 SEP3, just as the latest Challenger 3 iteration vastly improves upon the earlier Burlington matrix. This continuous evolution means that the tank is not a static platform, but a perpetually hardening shell, forcing adversaries to invest in increasingly complex tandem charge warheads or ultra-long rod penetrators, munitions designed specifically to defeat the very principles of layered composite protection.
Chobham did not end the armored arms race. It merely escalated it to the level of material science, where the quiet genius of the chemist and the physicist replaced the brute force of the metallurgist, ensuring that the tank remains, for now, the ultimate fortress on the modern battlefield.
If the introduction of Chobham armor marked the dawn of the composite age, the integration of exotic, high-density materials signaled its brutal maturity. The arms race between the armored vehicle and the anti-armor projectile is a dialectic of violence, where every defensive innovation spawns a more lethal offensive countermeasure. While composite ceramics successfully managed the threat of the heat jet, the response from ordnance designers was swift and decisive. The perfection of the long-rod kinetic energy penetrator. These armor-piercing, fin-stabilized discarding saber APFSDS rounds, often little more than immense high-speed arrows of tremendous density, required a new, even more resolute defense. This need ushered in the age of depleted uranium armor.
Primarily integrated into the successive iterations of the M1 Abrams series, particularly after the Gulf War validated its necessity, DU became the apex predator in the world of passive defense. Depleted uranium, a byproduct of the uranium enrichment process, possesses properties that are almost supernaturally suited for ballistic resistance. It boasts a density approximately 5 times that of steel, making it ideal for maximizing mass within the confined volume of the tank's critical frontal arc. When integrated into the Chobham matrix, replacing or complementing certain steel and ceramic layers, DU panels act as the ultimate kinetic barrier. The mechanism by which DU resists KE penetrators is both simple and profoundly effective.
Its sheer density requires an incoming tungsten or steel penetrator to expend a colossal amount of energy merely to displace the material.
Furthermore, DU exhibits a unique characteristic known as adiabatic shear localization. When struck by a high-velocity projectile, the intense localized pressure creates extremely high temperatures. Unlike steel, which might deform and allow the penetrator to tunnel through, DU shears cleanly, forming microscopic cracks that dissipate energy across the panel rather than allowing it to concentrate. This fracturing process causes the penetrator itself to wear down rapidly, blunting its tip, causing internal stress, and ultimately fragmenting the rod before it can fully traverse the armor stack. In the critical head-to-head engagement, DU provides the decisive advantage, a final, insurmountable wall of highly engineered material science. Concurrent with the deployment of DU, the necessity of protecting the tank's less armored flanks and turret roofs led to the widespread adoption of explosive reactive armor, ERA. ERA, primarily pioneered by the Soviet Union and refined extensively through systems like Contact 5 and later Relict, operates on a fundamentally different dynamic principle. Instead of absorbing the threat passively, ERA actively counters it with a controlled detonation.
Panels consisting of an explosive sheet sandwiched between metal plates are affixed to the tank's exterior. When impacted by a shaped charge or a kinetic penetrator, the explosive detonates outwards. For heat warheads, the explosive force disrupts the integrity of the jet, sharing it into ineffective pieces. For KE penetrators, the dynamically moving metal plates impact the rod sideways, forcing it to yaw or tilt, drastically increasing the effective thickness of the underlying passive armor.
The sophistication of modern ERA, specifically the advanced third-generation systems like Relict used on Russian tanks, moves beyond simple anti-heat capability. These dual-action modules are designed to function against both heat and tandem charge warheads, which feature two explosions, the first to prematurely detonate the ERA, the second to penetrate the exposed primary armor. Relict employs multiple, tightly packed layers of reactive elements designed to defeat both stages, providing a robust, though still external, defense. This technology allows older or less heavily armored tanks to achieve a survivability envelope approaching that of the heaviest composite armor systems. Meanwhile, the West has also embraced advanced applique armor, including non-explosive reactive armor, NERA, and specialized composite modules like those seen on the Israeli Merkava series and various upgrade packages for NATO tanks. NERA utilizes layers of rubber, plastics, or other viscoelastic materials inserted between steel or ceramic plates. Upon impact, the compression and rapid expansion of these layers exert significant pressure on the penetrator or jet, achieving a disruption effect similar to ERA, but without the logistical and safety risks of external explosives. This continuous innovation ensures that the tank's armor scheme is never static, but a living, breathing defense adapted specifically to the theater of engagement and the predicted threat. The relentless pursuit of hardening the shell has transformed the modern tank into a marvel of applied physics and material engineering. From the classified geometries of the Chobham matrices to the density of the DU core and the dynamic counter-explosions of ERA, the modern tank is protected by a layered defense system.
It is a calculated equation of failure, forcing the enemy projectile to fail at multiple predetermined stages, first through disruption, then through sheer density, and finally through dynamic counterforce. This complex architecture is what allows these metallic beasts to survive catastrophic battlefield damage, transforming them from vulnerable machines of war into near indestructible mobile fortresses, ready to shoulder the most intense violence the modern battlefield can muster.